Okay, so we'll go ahead and get started. Welcome, everyone. Thank you for joining us for another week of molecular networking things and GNPS things. So mostly leading it today will be Emily and Morgan, and I'll just kind of chime in here and there. But they'll help you get started, taking you through the very basics of using GNPS for creating your very first molecular network. So for those of you who just have data coming off your mass spec and you're like, well, I don't want to do anything fancy or hard. A lot of what we do in Peter Dorstein's lab is we start off here as a very quick glimpse at looking at the molecules we can identify, as well as broadly characterizing the chemical diversity. Of course, you can, as the research progresses, there's other tools, other ways to look at it. But this is one of the first and easiest ways for us to kind of get a glimpse of what's going on. So again, feel free to ask questions in the chat while we're going through this. And we'll have this all recorded and up on YouTube within the next 24 hours. So without further ado, I guess Emily, or I don't know who's starting, but one of you take it from here.
Morning. So I'm Morgan. I'm a staff researcher in the Dorstein lab, and today I'm going to walk you guys through, basically we're going to create a GNPS account if you haven't already, and then we're going to submit a classical molecular network job together. Okay, I'm going to go ahead and share my screen. Okay. Sorry, there's a little lag. Okay. So we have slides to go along with this. So if you get lost at any point, we also have these features on our Zoom where you can tell me to slow down or speed up, or you can raise your hand as well. So if at any point you are behind and need help, just let us know. You can also just chat and let us know if you get confused at any point. So yeah, we're going to basically make a GNPS account, and then we're going to submit a molecular network job. We're also going to be using public data. So this MSV like 00, this number right here, we're going to use it later if you need to keep track of it. It's in the slides. We'll go through that together. So if you go ahead and head to, this is going to be a hands-on tutorial too, by the way. So if you go ahead and head to the GNPS page, if you don't have an account, there's a register new account button at the top, which will take you to here, and you can really quickly just go ahead and make an account. I suggest that you use an email that you access frequently, because that's how you receive your workflow jobs when they're finished. And then once you're done making your account, if you don't already have one, then we're going to go ahead and go back to the GNPS page, like the home page. And then we're going to scroll down, and I'll go ahead and show you guys what that looks like here. All right, I'm going to go ahead and move forward, but go ahead and chat the group if you are needing any help or need to slow down. Okay, so from here we're on the home page, and I'm already signed in, but if you scroll down, you'll come to molecular networking, and then we're going to click on create molecular network. Okay, and then to start, I always just put in a title. It's basically whatever like meaningful title that helps you keep track and keep your work organized, but I'll say GNPS workshop, classical molecular networking. Okay, so we'll give it a title, and then we're going to scroll down to selecting input files. So really any of these will take you to this pop-out window. So you can just click on one of them. And then now we're in our directory for being able to add files that we want to run our network on. So right now we're in select input files, but when you want to access public data, you can go to share files right here. And today we're going to be using a massive ID for a Streptomyces dataset. And the number that we're going to type in to import data share is MSV 000082622. And then you're going to hit import. So I've already added this to my directory, so I'm not going to hit the import right now, but you'll hit import and then you would see it appear on the right side. And then in order to access this data so we can select it for a network, we need to go back to select input files. Sorry, I see there's something in the chat. Does it matter if I mix data taken in both positive and negative? I've never mixed different modes of data before. I've only ever run like a positive and a negative network. Ming, if I'm correct,
Yeah, so
discussion about this, right?
Yeah, so thank you, Ben, for asking the question. So generally, one of the operations we do right now in molecular networking is we collapse redundancy. So generally, there's no the spectra between positive and negative data, they'll be quite different. So what you can do is if you throw both of them in there, your positive and negative data will broadly segregate amongst themselves. And then it'll basically create separate subfamilies of molecules. So you can do it. We generally don't. What we tend to do is generate positive and negative networks separately. And then we have a follow-on workflow that at least somewhat intelligently tries to combine them. And then that makes a little bit more sense than throwing it all into one pool. So yeah, that's kind of how we approach it. And Emma, the question about different voltages, it's kind of along the same lines of if your 20 electron versus your 40 electron volt, if the spectra look drastically different, then they're going to self-segregate. Especially, this becomes an issue if you have the same molecule collected under different energies. And I guess this is generally a problem on Agilent instruments, so correct me if I'm wrong. So what we actually, Osama, he's here somewhere, he actually runs this issue as well. One of the recommendations we provide is, well, let's just filter to one collision energy, pre-filter it, and see how that goes. But that kind of throws away data. Another alternative and kind of gets it on par with other platforms that does a collision energy ramp and then merges this tandem mass spectra together is you can, after acquisition, you should be able to merge it in some software. Maybe MS Convert will do it, or ProteoWizard will do it, but then you kind of merge it and simulate a ramped collision energy, and then it's all good. But one of the caveats as to this workflow is we don't actually respect that the same precursor could have been fragmented with different energies and intelligently use that information. So we would recommend a little bit of pre-processing, one of these two ways, in order to kind of get it into the same kind of what we usually expect from molecular networking.
Okay, great. Thanks, Ming. So I'm trying to keep an eye on the chat as we go. Just to go back for anybody who missed that, we're importing the massive ID MSV, and then it's 4 zeros, and then 82622, and then you'll go ahead and click the import button. I'm not doing that because I've already imported it. And then once you've imported, we're going to go back to select input files. And then you should see it appear in your directory. Sorry, let me just move this over. Okay, so to open the folder, we're just going to click on this. And then, sorry, I had this open already, but basically the typical format for organizing a massive ID is you would put your like MZXML or MZML files into the peak folder. And so to access this data, we're working with 2 different strains of Streptomyces, and these are the data files that we're going to be putting into our network. So just to stay consistent with the slides, because if you go back and look, I'm going to put these in kind of a funny order. So also just to show you, okay. So basically these are the 2 different MZXML files, and then there's 2 in this folder as well. But to add to our selected files section, you can actually just click on the folder. So I'm going to click on Streptomyces roseosporus. Sorry, there's probably other people who can say this better than I can. And then you're going to hit Spectrum Files G1 with this little green arrow, and it should appear in your selected files section. We're also going to add this other strain. Okay. Sorry, I think we'll have to come back to some of these questions. I'm going to keep going with the demo, and then it might feel like I'm doing a lot of stuff right now, but we're going to walk through this in more detail, so hopefully it makes more sense. Then I'm going to select this other strain folder, which has 2 files in it as well. We'll go ahead and hit the Spectrum Files G2, and that should appear in this second group. And then once your 2 folder strains are in there, you go ahead and hit Finish Selection, and that takes you back to your like workflow page. Okay, so now you can see right here we've selected our folders. A lot of the time, the default settings for this workflow are usually sufficient, and as you become a more experienced GNPS user, you can start to play around with the parameters. But today, so again, to stay consistent with the slides that we've provided to you and the like in-browser data visualization that we're going to do, I'm going to change a couple of parameters here. So right here, we're going to go to Advanced Network Options, and we'll open it. And then we're going to change the minimum pairs cosine to 0.65. And then we're going to change the minimum cluster size to 1. So I'm just trying to keep an eye.
So one thing that you can show, there's a question about how can you choose a particular library to run with the molecular network. So you can show that, yeah.
Okay, so I'm just to show how to add a library, because that seems to be one of the questions. And I apologize if I'm not seeing everybody's right now. I'm trying to keep an eye on both. But if you didn't get your question answered, you can we can bring it up again. There's going to be a lot of discussion here. I'm happy to try and go back through. So for a library, basically you would have access to spec libs, right, Ming? When your account is
there's
created?
a default. Everybody has that shared. So by default for the libraries, it's everything in here. This is all the public mass spectral library data. Generally, you won't have a reason to change that selection. Unless there's private spectral libraries at GNPS, which you will not have access to for licensing.
I guess unless you created it yourself, but we also usually don't fully support private libraries, so we eventually try to work with users and make them public. But if you were to if you had I guess a private library that you created yourself, then you would go ahead and just select one of these. Like it would be your actual library that you would have input into your directory, and then you would put it into the library files by selecting there. So hopefully that answered the question. Okay.
So generally, yeah, again, it's possible. That's how you do it. You generally don't need to. So, and I think there's questions about there's other libraries that are private, such as NIST, that you know, of course, that we use kind of internally as a lab, and we just cannot share that publicly due to copyright reasons. We are figuring out kind of our general policy, but if you can prove that your institution or your lab has purchased those, then we can go ahead and grant you access to some of those things. But it's kind of on a touch and go basis where we don't really have an official policy on that right now. We want to be a little bit careful.
Okay, thanks, Ming. Okay, but definitely keep the questions coming. This is great. This is helpful, and then I can also go back and show people. Also, I guess one thing that I'll just note is if you are clicked on multiple things and then you select the input file, it'll drag it over. That happens sometimes, but anyways, okay, so we have our spec libs is already like preset and in there. We put our files in and then we finish selecting. And then right now we're updating a couple of the parameters. There's the main pairs cosine that I changed to 0.65. And then the minimum cluster size has been changed to 1. And then the next thing that we're going to change is we'll scroll down to advanced filtering options. How am I doing speed-wise? Pre-processing required for these. I think there's another question that I think I might need you to answer. Is this pre-processing required? Which software do you recommend?
So yeah, Whitney, so if you've run it with stepped collision energies, generally what the instrument does is it merges it into a single scan. If that's the case, you don't need to do anything. If it keeps the different energies separate, then you will need to do something. So again, one of the things we mentioned was you can take it and you can just filter to one collision energy, and then just, that's it. You maybe 20 or 30. Alternatively, there's software, I think ProteoWizard should do this. I'm not really sure. You should be able to merge them, but that operation is a little trickier than it actually seems. So those are kind of two recommendations. We haven't explored the merging post-acquisition fully, just because all the platforms that we usually use, Thermo and Bruker, they do this automatically in their vendor software. So if you have a different system that you're running into problems, and there's, yeah, Emma just, I guess, okay, this should do it on the Thermo automatically. Let us know, reach out to us after this, and then we can take a look at the data and see what we can figure out.
Great, thanks. Okay, continuing, and you guys can just keep interrupting me if there's more questions that I'm missing. So the next options that we're going to change are the advanced filtering options. So if you just open, we're going to click on Don't Filter for the filter precursor window. And then again, Don't Filter for filter peaks in 50 Dalton window. And then last, we're not going to filter the library. Okay. And then basically at the bottom, the email account that you added when you made the account, or I guess, yeah, when you first made the account, should appear at the bottom. And if you, I don't know, if you have a more recent email that you use, you can just update right there. But then otherwise, we're going to go ahead and click Submit. And I know this probably feels like a lot of detail here, like we're changing a lot of different things, but again, we're going to go over basically what we're doing, and we're going to go over and explain molecular networking. But we just want to get this job submitted. So if you are following along, go ahead and submit the job, and that will be running while we're discussing, and we can be answering questions. So I'll hit submit, and then it will take me to this page, and this is like the job status page. And I'll receive, like, you can keep an eye on this like file, but you should receive an email when it's finished running. And then with that, I'm going to pass it over to Ming to walk through some more of the molecular networking details.
Okay, awesome. Let me share my screen. Just a second. Share screen. Okay, so is it? Okay, so there's a lot of slides here. Okay, I skipped ahead a little too much. Everybody can see my screen? Yes. Okay. Well, I guess nobody can talk. So we talked about some of this stuff. So just as an FYI, there have been some questions about what we actually ran and just understanding those specific details. And so what we just ran was there were two sets of data. One where we looked at all the tandem mass spectra from a Streptomyces strain, I believe it's the wild type, something like that, as well as a very particular strain that we had in the freezer. So when we look at all the molecules we can from the mass spectrometry between these two strains, we want to ask the question, what's different between those two strains? And so molecular networking is one of the ways that we use to compare those differences. And so one of the things that molecular networking gives us beyond just asking, is this single molecule present or absent between these two strains, it helps create a nice scaffold by organizing the putative chemistry and being able to show us, well, there's a family of molecules here that is unique to this strain. There's a family of molecules that is not in this other strain. So it helps simplify and visualize how we actually look at this data. And so what I'm going to get into right now is some of the intuition on how to think about creating these networks and what we actually rely upon to create these networks. So any questions so far? Okay, well, it's not a speak now or forever hold your peace thing. So so the very basic idea, so what we have here on the slide are two molecules. So again, my background, I'm a computer scientist. I don't actually know things, but I will speak like I do, so you can kind of roll your eyes a little bit sometimes. But what's happening here is there's two molecules that are quite similar. They're not exactly the same, but they are quite similar. And so the idea is, well, if they differ a little bit, in this case, they add on a methyl group or extend this lipid tail. And so the idea is, because they're so similar, when you put them into a mass spectrometer and you fragment them into pieces, because most of the structures are the same, they're not going to be exactly the same in terms of fragmentation, but they're going to be very similar. And so that's kind of the core idea here, is that if two molecules that you put into the mass spec are similar in structure, we hope that the change in structure does not perturb the fragmentation significantly, and thus what will happen is that the fragmentation will be, the shape will be similar, but there's going to be some differences. And there's an alignment scheme that compares two tandem mass spectra in GNPS that will account for these changes. And so the changes that happen here, if there's a single change in structure, is that a lot of the peaks will be, a lot of the fragment peaks will be exactly the same in mass, but some of them will be shifted because they will have the modification. And so this shift will correspond to the mass of that modification. And so you can kind of see that here, these get shifted over by 28 Daltons, these peaks on this right side here. But a lot of these other peaks for the core structure of this molecule, this core ring, they stay the same. And so yeah, so Peter's, and there's a question from Effie in the chat about, does this work for knowns and unknowns as well? The beauty of this, especially when we started, is it should work for even if we don't know the structure. So when we create the networks, we have no idea what the putative structure actually is. And so you can imagine, if they are, you can do the reverse kind of inference and that leap works most of the time if they are similar in the spectra. They putatively might be similar in their actual structure. And so when we started this, we actually just took all the mass spec data and created these networks, and we didn't even have any libraries or anything to actually identify with. So we were counting on it working in the absence of identifications. So that's kind of the straight intuition behind it. And so what you can do is now each of these spectra here represents a unique molecule in our data set. And then one of the things we can do is layer on extra information is try and identify what's in here. What are the molecules that are in here? So you could imagine that because you've organized all of your own data into these families, if you can identify families of related compounds, if you can identify one member of that family, that tells you something about that whole family. And so it really helps in this kind of knowledge propagation, especially in this world where knowledge about all the molecules and knowing the structure is quite limited. And just kind of giving you a historical background, back when we started, the libraries were quite small, and we could identify maybe 0.1 to 0.5%. These days, depending on the type of data, maybe 5% of the data. So still not great. So it's great to have this amplification technique. So you can identify one of the molecules, but then what you do is for every unique molecule in your data set, each unique spectra in your data set, what you do is compare it to all others. And you ask that question of, okay, this one spectrum, is it similar to any other spectrum in my entire data set? And so you do this full pairwise comparison. And then for the matches between spectra in your data that have high scores, then you put that into the molecular network. And the way we represent this is each circle represents a unique a tandem mass spectrum, and kind of to a first approximation, a molecule in your data. And then if there's a line between them, that means they match pretty well in the shape of the spectra. And then there's a few other criteria as people are asking in the chat. There's the similarity score, which we call the cosine similarity score. It asks, are the intensities of the peaks roughly the same? Additionally, there's a couple other match parameters that give us a little bit more control, and that relies on asking how many peaks between the two spectra actually match. So you can imagine, and the reason for this is if a spectrum or a molecule fragments very poorly and it generates perhaps just the precursor, that's not really much information. And so that if you have cases like that, you're going to have a lot of false positives. And so by default, we require 6 minimum peaks to match in order to make it into the network, as well as a cosine of 0.7. And so these are generally, it works out generally well, but depending on the type of molecules and how well it fragments, it might be too restrictive to capture it. So it's generally smaller molecules, under 300 Daltons, they don't fragment so well, and so you will need to adjust your parameters there. So I see a lot of questions. Emily, do you know if there's any that we should address right now?
I think you're good. The main questions were about the number of fragment ions, or I guess the matched fragment ions parameter.
Okay.
Yeah, and then there's just another question about positive and negative.
Yeah, everybody has positive and negative data now. So that's great. So there are, anyway, we'll follow up. Maybe we'll do a small workshop on that later, but specifically on positive and negative data. But again, it's important to think about this interplay between the number of peaks that match and how well the peak intensities match. And the third element in here is the false connections. So if you have really lax parameters, you can imagine you're going to get a lot of false positive connections. And so we actually have a paper about this relationship between the two. But generally, if you drop it to like 1 or 2 peaks that match, you're going to have a similarity in the intensities in the cosine score very close to 1.0, which means it perfectly matches. So there is this sliding scale trade-off between the two. So it's something to think about. So anyway, so we'll stop that there. And so just kind of high-level example of what you can expect to see. This is one example from some natural products, I think actinomycete extracts. And so these have been automatically annotated already for us. But you can see it groups different classes of molecules together. And so there was a question about, kind of in relation to how you would cluster BGCs. And so in a similar way, if you are familiar with recent tools such as Bigscape, they try to cluster BGCs, and here we try to cluster based on the mass spec data. And they're not going to have a perfect correspondence, but that's generally what we see. Similar families of molecules, so as a non-natural products person, I would presume that similar biosynthetic gene clusters would also produce similar classes of molecules. So we can see different families of molecules in this particular example kind of grouping together, so that if you can identify one single one, you can start exploring the chemical diversity around that. So again, we're actually going to revisit this example in the data that you actually just ran, and there's a little tutorial make you do stuff at the end. But this is when we actually published the GNPS paper. So one of the things we like to do with the tools at GNPS is we like to release them like way before we actually publish them. So when we actually published the paper, there have been many other creative uses of GNPS beyond this one, but we kind of showcased one example where we discovered some new molecules. And so what we see here on this right side is, again, each circle represents a molecule, and these lines represent similarity in fragmentation and hopefully similarity in structure. And so what we see here is these two different strains of Streptomyces that we networked together. And in green are the molecules from this standard Roseospora strain, and in this bluish color are the molecules that were unique to this DSM 5940 strain. And so we can see that they're kind of segregated at the bottom here. And there's some overlap. We can see some overlap in production. But what was interesting to us is we saw these consistent relationships between molecules produced by this known strain compared to molecules produced by this new strain that differ by 41 Daltons. And so we saw several different variants that also had correspondence that differed by 41 Daltons. And so I didn't actually do any of this chemistry work because it's beyond me. But after they did purification and NMR to figure out what the actual structure was. And when this network guided them into that hypothesis to chase this down. And whenever they actually solved the structure, they found that there was a substitution of one of the amino acids here. And that led to this 41 Dalton mass loss. And so beyond just having a single variant of that, we actually saw many of them that have this substitution that differ by the length of the lipid tail. So that's one of the examples that we're going to look at today. And then so hopefully that kind of gives you one of the ways that you can use this classical molecular networking to explore the diversity. I guess, okay, so that's the second part. That covers kind of the high-level overview of the molecular networking. I think, let me just check. So we're going to go through the details. Okay, sounds good. Who's Morgan or Emily? You're taking it from here?
Yep, I am taking it over from here.
Okay, so let me hop off the share.
Okay, hi everyone. So for those of you that don't know me, my name is Emily Gentry, and I'm a postdoc in Peter Dorstein's lab. My background is actually in synthetic organic chemistry, But then I joined the lab about 1.5 years ago, and so now I've been learning all the tricks of GNPS and mass spec in general. So today I'm going to take you through data visualization of the job that we just submitted to GNPS. So I guess maybe first, can we take a poll to see if people's jobs have finished? Or I guess yes, finished. Okay, cool. So I guess then what we'll do in this section is we will explore the data that was just analyzed using the GNPS Classical Molecular Networking workflow, and how we're going to be visualizing our data today is by using the GNPS in-browser visualization tools. So we're only going to be using sort of the GNPS interface to interact with our data today. So I know that some of you probably know that Cytoscape is also a very useful data visualization tool for molecular networks, but we won't be covering that today. So I'll just tell you a little bit about, I guess, the pros or the benefits of both types of data visualization. So the in-browser data visualizations that we're going to be using today, I think you'll find that they're good for sort of exploring the molecular networks in more detail. So if you have certain like subnetworks that you're really interested in, it's good for exploring those and actually looking at the spectra. But then for Cytoscape, that's really useful for a more, I guess, broad and bigger picture exploration of the molecular networks. So without further ado, the objectives for this section are then to use the GNPS online interface to do our data visualization. And within that, we will look at library identifications and sort of assess the quality of a library ID. And then furthermore, we'll just explore and play around with our molecular network and sort of see what we can discover. So I hope to show you some sort of tips and tricks for in-browser visualization. So how you will actually access the job is if it didn't finish running for you, then you can just click on the link shown at the bottom of slide number 33. Alternatively, hopefully your job ran already and you can just go to your GNPS homepage and then click on the Jobs tab at the top of the page. So this will take you to a page that looks like this. Your page might have more or fewer jobs, but it should be the last job that you ran, hopefully. So just click on this status done. And that will take you to this green page, which is the job status page. And here there's going to be a lot of different links that we can click on, but we're just going to focus on sort of these top links here. So first, what we'll do is we'll go through how to actually look at the library hits within your data. So one way that you can do this is by clicking on the View All Library Hits link. And so this will take you to a page that shows you all of the library hits found within your data. And so for us in particular, since we were looking at Streptomyces strains, maybe we want to look at for some peptidic antibiotic compounds. So let's just go ahead and search for the suffix mycin. So here you can see we have uridomycin, arilomycin. So what we want to do now is let's just actually check the quality of a library match for one of these compounds. So I'm going to click on here, arilomycin's mirror match plot. So what this allows you to do is directly compare the MS spectra that was found within your data to the library MS spectra. So on the top in black is the MS/MS spectra that was found in your data. And then on the bottom is the MS/MS spectra of the library. So, or of the library compound, in this case, arylomycin. So you can see here that actually for this compound, we have a pretty amazing mirror match. It's pretty beautiful. So we can sort of with confidence say that arylomycin is indeed found in our data set. So that's sort of how you can check the quality of a library ID. And you can go ahead and sort of play around with other library compounds that were found within the data set or your own data set. But for now, I will return back to the status page to show you some other tricks. So another tab that is really helpful. Okay, let me check. Sorry, let's check on the chat. Okay, so I guess one of the questions is, could you talk about where the library matches come from? So these come from the libraries that you select within the submission or the job submission for your molecular network. So in this case, we selected static libs, which includes a number of different libraries. So it's querying the spectra that's found in your samples against the libraries that are selected in that job submission form. And I guess another question is, what is silver, gold? Here, let's go back to this. What does silver, gold, bronze, et cetera mean? So gold is sort of the best rating for a library spectra. So this rating can only come if you have, I guess, a secondary analytical means of confirming the structure of the compounds that that has that MS/MS spectra. So say you purify a compound, so you isolate a compound and you take an NMR spectra, and then you take the MS/MS spectra. So that MS/MS spectra would be a gold match or a gold library class. Bronze is usually, I guess, what most library IDs are, and that's sort of like you should take it as a putative match. Because there's not an NMR spectra or something else that confirms the structure of that match.
Yeah, so it's any community annotated library and spectra or community annotated spectra.
Yeah.
But in general, I've never seen anybody filter. So you can actually search the site ahead of time to search with bronze, silver, or gold. So far, nobody has ever done that. You can filter at the end if you wish. So it's really up to the user how they want to leverage it.
Perfect. Thanks, Peter. Okay. So I think that hopefully answered everyone's questions. Keep chatting away. Yeah, so I would say that your best way of actually getting confidence in a match is really checking that mirror match plot. And that's sort of the best way that you can confidently say that, you know, it's a good match. And I guess you can sort of decide whether you need to follow up on that annotation or not with I guess a standard if necessary. Okay, so another useful tab is this View All Clusters with IDs tab. And this will take you to a list of all of the nodes within your molecular network. And so each node of your molecular network is assigned a cluster index ID number, which is shown here. And so here we're just gonna filter this table and look for, let's say, we'll look for the stenothricins. So here we have a list of different stenothricins and their corresponding cluster index numbers. And then here, I guess a few different buttons to point out are this search spec button, which is pretty cool. And that will take you to a link out that brings you to a massed search, or a massed search workflow form. So for those of you that came to the workshop last week, you probably are familiar with this, but this allows you to actually query the spectrum against the entire GNPS database and find out where this compound is found in other GNPS datasets. So that's a pretty cool button. And then another one that you might have learned about in the first workshop, I guess maybe 2 or 3 weeks ago, is this button, this Annotate to GNPS button. So here you can actually go to a link out where you can add an annotation to the library. So that's also sort of a useful button that you can access from this, this View All Clusters with ID tab. So then what we're going to focus on here is this View Network button, and this will take you to the sub-network of the stenothricin family. So just a few little tricks that I want to go over. So just the basics, I guess, are you can change the node labels here. So you can use the cluster index numbers. You can label them by the parent mass or the library IDs. And then something to note is you'll notice that the library IDs are all in blue here, whereas the unannotated compounds are in gray. So that's just an easy visual way to sort of look at which compounds are annotated within your subnetworks. And then another thing that you can do is change the edge labels. So you can label your edges by cosine score or delta MZ to try to sort of get some structural information on the for your nodes or for the unknown nodes. And then another thing that you can do within this in-browser visualization is you can actually draw pie charts based on the groups that you input into the workflow at the start. So if you remember G1 here, we input as Streptomyces roseosporus, I believe. So if we just put draw pies, we'll see that some of the nodes are only in red, and this represents the compounds that are only seen in, that are only seen in G1, or that roseosporus strain. And so there's quite a few compounds that are unique to that roseosporus strain, but then there's also compounds over here, the stenothricin GNPS2 match, which is unique to the other Streptomyces strain. So just a really quick way to visualize sort of, you know, what compounds are seen in which samples or which groups of samples. Okay. Ming, is there anything in the chat that I need to address?
Oh, Peter's all over it.
Okay, cool. Thanks, Peter. Killing it.
I'm having fun.
Okay, great. So that's the pie charts. And I guess I just want to show you a few other tricks that you can do. So one thing that I find to be really helpful is direct comparison of the spectra between, or of different nodes. So you can, in this in-browser visualization, you can really easily compare spectra between nodes. So one way that you can do this is by simply clicking on an edge between two nodes. So if you click on the edge, then you'll see that it actually pops up the two spectra associated with the nodes, I guess, on either side of the edge. And so then here, you can also click on this Align Spec button, and this will allow you to directly compare the spectra and really see which fragments are different and which fragments stay the same. So here, the fragments in blue are the fragment ions that are shifted or different from or between the two spectra. And the ones in blue, or in red, sorry, are the ones that stay the same. So here you notice that a lot of them are shifted by 14, which could be maybe a methylation. So that's an interesting way to sort of compare spectra, but you can do this with any two nodes within a subnetwork. So how you do this is if you just left click on one node, it will populate the top window here. And then if you right click on any other node within the subnetwork, it will populate on the bottom panel here. And then you can do the same thing. You can align spec and sort of see how they compare to one another. So then another tool, or another, I guess, trick to show you is that we can also highlight edges based on their delta MZ or based on their cosine scores. So let's try the highlighting maybe the edges that have a difference of 14, a delta M over Z of 14. So here, if you just input 14 into the box and then press this refresh button, it will highlight all of the edges that are represented by a delta M over Z of 14 in red. And so this is really useful for seeing sort of what modifications are in your subnetwork that you're interested in. Another thing that you can do is, so I'll just do that. Another thing that you can do is also actually look at or try to, I guess, identify nodes that have a common fragment ion. So let me just show you an example where this might be useful. So I'm going to go back to the PowerPoint or to the slides. So here, if we look at the stenothricin family with this lysine fragment in it, we have sort of this stenothricin core has an M over Z value of 894. And so you can imagine that this 894 would be a common fragment ion in the stenothricin family. So one thing that you can do within the in-browser visualization is you can actually put in 894 and search which one has that common fragment ion. So how we're going to do this is first you actually have to download node MSMS Spectra. So you have to click on this button with the arrow here. And then you can put in 894 and click on this refresh button. And what this will do is, oh, sorry. Okay. So what this will do is it will highlight all the nodes that contain this common fragment ion of 894 in red. And so this is a really good way to sort of really quickly visualize which ones might be a part of the stenothricin family that has this lysine fragment, or this lysine component. So I think that is it for all the tips and tricks that I want to show you for the in-browser visualization. So I guess the next order of business is we actually have some workshop tasks that you can practice using this visualization, this in-browser visualization with. So we're just going to pose, I guess, these 4 workshop tasks. And normally we have these workshops in person, so people can work in teams. But this time, I'm sorry. You know, hopefully you can do these on your own, and maybe we'll give you a few minutes, maybe 5 minutes. Ming? 5 minutes? Cool. To complete these tasks. And hopefully this will generate some good questions about using the in-browser visualization and other things. So we'll reconvene, I guess, in about 5 minutes to go over these workshop tasks. But in the meantime, I think we can maybe open the floor to some questions.
Any questions? Feel free to ask. Either, I mean, I guess a lot of people have been asking on the chat. Oh, there's one question, Emily. I don't actually know fragmentation. So they ask, how did you know the MZ of the core molecule so quickly?
Yeah. So, well, I knew it so quickly because it was on the slide, but, but yeah, so how you can sort of figure out that, the core, M over Z value is, by actually drawing it out and figuring, the M over Z of this core minus the R value.
Yeah, so Ming has a feature here somewhere that you can display the 894 in this view. Can you highlight that, Ming?
Yeah.
Or
No,
Emily?
Emily can. Emily knows it. Yeah.
So there's the feature. Sorry if people didn't catch this. So let's just actually go back. Okay, so how we are going to highlight this is first we're going to load the MSMS Spectra into our subnetwork. So you have to press on this like button with a sort of looks like a download button, and then you put in the 894 into the blank here, and then you're going to hit this like refresh button, which will display and highlight the nodes that contain that. So if we want to do that, so first we're going to hit the download button, and then we're going to put in the 894.
Can you scroll up a teeny? I think it's hard to see. I don't know if everybody's dimensions are the same. Yeah,
okay.
In your actual, like the large window.
There we go. Can't really. Okay.
That's perfect.
Yeah.
At least for my screen. I don't know about everybody else's, but it's hard to see the bottom. Thanks.
Sorry, everyone. And so
I think Jing asked what she meant was how to determine which one is the core just from the network. And actually from the network itself, you cannot determine what the core is. You need to go to the structure, look at the MSMS, and then what we do typically is going into ChemDraw and looking to see what part of the molecule matched to that particular mass. And then once you know this, then you can go back and say, okay, which one of these molecules or nodes have this particular core? And so you need to decide what you want to look at in the network. Does that help, Ying?
Sorry, I have one other question regarding this. You have a node MS, the same place that you were talking here, that you there is the button of refresh, but next to that, when you click on it, it actually gives you all the the peaks. So there, I mean, here it's really complicated.
Yes.
Yeah. Okay. For my case, it was really like easier.
So yeah, so here is pretty complicated, but actually you can see that the 894 sort of spike as a peak. So that's one way that you can also look for maybe the most common fragment ions within a subnetwork. That's a really good. It's a really good point. Yeah.
Okay, there's a couple of questions about in-house dereplication and silico dereplications. These will be separate workshops, but then also in terms of in-house MSMS dereplication using classical molecular networking workflow. So that's essentially when you do a molecular network and you make sure that you turn on matches against reference libraries. That's essentially the dereplication. So it's already part of the classical molecular networking workflow without you having to do anything else. So it searches all the publicly accessible libraries for you.
Yeah. So another question that we got was, I guess, when do we use this versus Cytoscape? And so I personally, I actually use this quite a bit, and that's because I like to look at, actually compare the spectra within subnetworks. So that's like primarily when I use the in-browser visualization, is really when I want to look at the spectra within a subnetwork and compare those. When I'm using Cytoscape, it's more to look at the whole network as one. And when I want to map sort of different metadata categories, Cytoscape is really useful for that. So I don't know if that answered your question, but yeah, this is really good for in-depth analysis of the spectra within a subnetwork. Yes, for sure. This is also possible to use for publication. And actually, Ming, where's the link out for the nice like API?
Oh, you mean wait.
For like mirror plots and stuff, or for like.
Okay. So you have a slightly old. This example is slightly old. So, well, I guess there's several ways for publication. So you can take a screenshot of your screen, which is not particularly great. There's also a screenshot button for just the network that you can download. I think, Emily, it's right at the top, to the left.
This one? Yeah.
Yeah, so you can download that as a PNG. So it's not particularly great for publication. To the right of it is a GraphML file, which you can download and open in Cytoscape, and then that's pretty good for publication.
So this is also, sorry, can I interrupt and say, this is also a good way to look at subnetworks. If your overall network is huge, you can go in, look at a subnetwork that you're interested in, and download the GraphML, and then pull that into Cytoscape.
Yeah, so definitely for the full network, I guess kind of going back to Emily's question, but Cytoscape is great if you want to look at the full network to prioritize where to focus on. And then when you're focusing on it, you hop back into the browser. But in terms of nice ways for publication, this is one way to view the network. Additionally, we have some new tools for visualizing spectra themselves that are vector-based, as well as looking at mirror plots that you don't have to take a screenshot of your monitor, and you can just there's a new link out. You all should have it. And then for library search, as well as all the elements in the network, all the spectra in your network. So it'll be high resolution that you can pull directly into Illustrator for publication.
Okay. Oh, so there's a question about should I expect the same metabolites to be annotated within the molecular networking workflow and the spectral library search alone?
So that's a good question. Generally, yes, but there's several caveats in this. So one of the things that we do in the molecular networking is we first cluster your data. So this means reducing the redundancy of the same compound. So as we see in the thread, there's it's not perfect. As well as we do some thresholds in order to throw out things that we suspect are noise. But generally with this throwing things out, you throw out some real molecules as well. That's just kind of the nature of the beast. And so if you do the library search and what's remaining, you will identify generally a subset of what you would have found if you've done library search by itself on all the MSMS data. But it's in the service of data reduction, just because you have tens of thousands of molecules and a lot of noise, it's not, you need to prioritize somehow. That's kind of the trade-off that we've gone with. But if you care specifically about identifying known compounds and prioritizing it from that particular fashion, I would recommend you do the library search first to see if whatever you expected is there. But if you're kind of doing a more exploratory hypothesis generation approach with molecular networks, then do that as a second approach.
Yeah, so then there's also a question about how the Molecular Explorer identifies compounds that, so the Molecular Explorer is a tool that you can find on the page, and how this sort of differs from molecular networking, I guess. So Molecular Explorer, sort of similar, it's masked, right? It's the same as
Yes,
masked.
so this needs a little bit of an overhaul, but yes, it's effectively, we've taken all the public data, we've created networks out of it, and we have done library search on everything. So this kind of summarizes it in a very curt way, but it tells you for each molecule what data sets is it found in, and I believe it also might tell you some of the analogs at bare and which data sets it's found in. So this is for over everything, all the public data, but then when you do molecular networking, it's going to be on a subset of data that you select. So however you choose to select that. So it's a difference of scale, it's a difference of depth.
So another question is, when would you use classical molecular networking versus feature-based molecular networking? I guess I usually use both. I use classical molecular networking as a first sort of exploratory look at my data set. And then I'll use feature-based molecular networking to sort of refine and get, I guess, better quantitation of compounds. So yeah. And that way you can also, reduce the redundancy of the nodes. And you can actually see isomers of things. So, feature-based molecular networking relies on retention times as well. And so you'll get sort of, I guess, a better idea of how many features are actually in your data set.
So one thing regarding the feature-based is it relies on some feature detection software. And this is generally a highly manual tuning step. And so that's a pretty big downside. And in general, even though you get isomers, you must have a good peak in the chromatogram, which drastically reduces sensitivity of molecule detection. So generally the feature base is less sensitive, but if you have a ton of data, you need to do some data reduction somehow. So it really depends on your particular application. If you have like 1 or 2 files, it's probably not meaningful. But if you have a couple hundred to a couple thousand, that is very rich and you just are overwhelmed with the data. That's one way in order to really start pruning out better signal from it. But again, it depends on your question. Oh, there's another question here about different groups. If you have a couple hundred files. So as Emily had shown and Morgan had shown, there's 6 default groups you can put things in. It's like G1 through G6. I built that merely for my convenience. I never wanted to fill out like files describing the sample prep. I just knew there are 2 categories, and I didn't want to write a spreadsheet.
Hi, Annalise and Helena.
Okay.
Oh, sorry.
Yeah. So one of the things you can do in the documentation, there's a metadata format that you can say, it's a spreadsheet that says this file name is part of this group. And if you put that in there as a metadata input, then it'll respect that. So you can have in this particular case, you can say this file is from strain 1, this file is from strain 2, and you can easily specify that in that fashion. But again, the grouping G1 through G6, purely a convenience feature, but it's the easiest one to teach. But if you have more than 6, go ahead and do it that way. Even if you have less than 6, it's probably better to do it that way, just because then you actually remember what the groups mean, as opposed to trying to write down on a post-it note, G1 means this. And then the question is it possible to see the networks of G1 and G2 separately? So generally, we network everything together. If you want to see separate networks for different files, you can just run 2 networks. That's generally what we would recommend. The different subgroupings in the interface is just to make it easier to enter some kind of cohort metadata without actually writing a file if you just got the data off the instrument. But that's generally what we would recommend. And one of the things you can do is in Cytoscape, you can visualize everything. So you can color it like Emily has it here, red versus blue, and you can just kind of color it that way and see how it goes. Yeah, so Jing, as you're seeing here, this is relative quantification data, right? So we know red is G1 and blue is G2, and we draw the pie charts on it as well. And so these pie charts are a gross way to measure the differences between these 2 groups. And so it's not super quantitative because the way we do it is based on spectral counts in classical molecular networking, but it gets you there. And this is based on whatever metadata you imparted, and we calculate this all automatically. If we're talking about feature-based, it does the same operation, except it actually bases it on area under the curve. So the relative quantification will be a little bit more accurate in terms of proportions and a little bit more granular there. So Emma, I think your question that you're asking it's kind of along the lines of blank subtraction. Is that how I'm interpreting? You have some features that you want to remove in your feature when you do your feature detection that you just don't want in consideration for the molecular networking. I think I've interpreted that correctly. Yeah, so what you can do is you can pre-filter upstream, whatever, you can do feature detection, and then you impart the filtered feature table into there's another workflow for feature-based molecular networking. And then there's a new update coming out where we actually respect that. So it's coming, should be out this week, but it'll respect that and it'll ignore those features for consideration in the network. So then you don't have to go mucking around in MGF files because that's a whole can of worms. So we trust users to delete rows in an Excel file, but not edit an MGF file. Recipe for disaster.
There's also a question, if I have a large number of data files, approximately 100 different extracts, how can I visualize different samples while having only 6 groups?
Oh, we already did that. That one is for the metadata.
Oh, you did?
You make a metadata file.
Oh, okay. Gotcha.
Did you address Emma's comments already?
Yes.
Okay.
And then there's a question about the difference between CCMS peaks versus peaks.
Okay, so this is a great question. So in public data sets that users like yourself submit, that you make publicly available, I think it's in the documentation somewhere, but anyway, nobody reads. So peak is what we consider open formats that users have uploaded. So if you have converted to MZML, or MZXML, generally we recommend MZML these days, that's what goes in peak. There's a raw folder as well that's just like the vendor formatted files. CCMS peak, however, so the CCMS stands for the Center for Computational Mass Spec, so that's kind of where I did my PhD. And that's that they provide the underlying infrastructure for running GNPS. And there they take, actually, well, I wrote this code, but they take this, the data that was submitted and they convert it to their own formats, just in case when users created the peak folder, they didn't have the right settings, they didn't centroid or things like that. So we try to do a reconversion of these files into what we think is more compliant open formats. So that's generally the difference. Again, it's not a perfect job. Sometimes we screw it up, and so that's what the semantic distinction between those two is.
Okay, nice. Should we take a look at the workshop tasks then? Seems like questions for now have lulled.
Or are there any questions regarding like the workshop tasks maybe, or does anyone want to go through like how any of the questions together, I suppose?
Okay, so Osama is, he's asking if he should choose the size of the data set with those sort of pre-populated like presets that are seen on the submission page. So you don't have to, you definitely don't have to. You can set the parameters yourself, and in fact, there's often no need to even change them from sort of the automatic preset parameters. But Ming, maybe you want to go into what small, medium, large means?
Yeah. So we put this in the documentation, but we should just link to the documentation from this page, but from the workflow input page for the relevant areas. But broadly, I guess maybe it's a little vague because small, medium, and large mean different things to different people. So generally what we mean by small is something under 10, 20 files. And the functional difference, there's really only one parameter that changes, and that's the minimum cluster size. So again, as I mentioned, we first cluster the data, so try to reduce redundancy of the same compound. And then we filter out clusters that we don't see multiple MS/MS spectra, or it's possible that we do that. And so generally the default is we must see an MS/MS spectrum twice in all of your data that you selected in order for it to be considered kind of real and for consideration of the network. So if it's small, we set that to 1. So generally we recommend, under 20 files. Anywhere between that amount and like a couple hundred, 300-400, you can use the medium data size, and above 400 to a couple thousand, we recommend the big data preset. So that's generally that's the broad range that we'd recommend. And so for the big data set, what we recommend, or what the filtration does, I believe it sets it so that you have to have seen an MS/MS spectrum 3 times in order to be considered to be part of the network. Everything else is just thrown out.
So to follow up a little bit on this, the MS cluster, if you set this to 0, which you have control over, it basically then does a molecular network with every MS/MS spectra with every other MS/MS spectra. And that would include noise, basically. If there's a spectra that is just noise, it would include that as well. And so when you do MS cluster and you set it to 2, 3, 4, 5, it means that you would need 2, 3, 4, 5 identical spectra in your entire data set. And so this is noise by nature is irreproducible. And so what that means is that it's essentially very aggressive filtering step for spectra that are reproducible. And so that is one of the consequences of this. And so it's a really nice way of cleaning up your data.
So Ben asked a quick question about if you do feature-based versus this classical molecular networking, about 50% of the metabolites are annotated. So there's a big caveat here in terms of how the feature finding was done. So there's, again, as we were saying, with feature finding, there's a big manual step to this. And depending on how you set some of the parameters, you can be very, very strict in terms of the filtration. You might end up with zero data at the end if you don't set it properly. So this is kind of, it's hard to answer this question about if you're losing IDs, if you're doing feature detection, which one should you trust? It really comes back to they're both it's a filtration technique, right? At the end of the day, that also gives you quant, but functionally for the ID side, it's a filtration technique. And so what you should trust depends on the question you're asking. If you really care to answer what molecules are in this data, you probably just care about doing library search and then going back to your raw data and verifying it, and at the end of the day, running some standards to clarify and verify it. So I'm not sure that the question, which one should you trust, between the classical molecular networking and feature-based, that's a particularly meaningful question, and one that we can actually answer. But the IDs that you get, those are a starting point for you to think about what's in your sample and think about propagating IDs. That's probably the best role into thinking about this.
So there's a question about Molecular Explorer. So Molecular Explorer is one of the, it's on the front page of GNPS itself. It's not really related to classical molecular networking. But Molecular Explorer is basically a list of any molecule for which we found an annotation, a spectral match against the reference libraries. And so, for example, the 13-dosinamide, we find it in 345 data sets in 29,203 files in those 345 data sets. And then you can view the data sets, you can, etc. And so basically what we have is we have MSMS libraries that are available, and we search all the publicly data sets that are publicly made available through GNPS. And so, so this is, all these have MSMS available. Maybe Leon can clarify what is meant by this question, but now you can basically find what data sets this particular MSMS spectra has been found in. Oh, Ming, where can he find the MSMS data for this?
Yeah, so there's a thing.
It used to be there.
No, it never was there. I don't think it was ever there. Anyway,
Right.
we collapsed it based on compound name, so to reduce some redundancy. So the underlying, you can look at the MSMS data in public data sets if you click on, I believe there's a link for the public data sets. So where is it? Explore. So if you click on Molecular Explorer, Emily, can you click on View Datasets? Yeah, perfect. So if you view datasets, now if you look at View Continuous ID Search, so this shows you the identification of this particular compound name in this particular data set. So now if you click on the left side, the spectrum icon, it'll show you all this information. So this is the way to find its connection to the actual public data sets. And then if you want to go back to the library entry, you can click on View Lib. So that'll give you the MSMS for the actual library entry as well.
Does that help, Leon? And you know, all these reference spectra are downloadable. So if you go to the spectral libraries, you can download all the spectra from all the spectral libraries.
And also, if you're a computational person, you want to churn through all this data, we've already deposited a summary of all of this information. So the networks, the identifications, the clustering for all of GNPS into a single data set as text files. So it's relatively easy to parse. So you can track everything back if you so choose and rebuild a molecule explorer if you want from that data. It's like 60 gigabytes, so it's not the smallest thing in the world, but it's all there relatively easily to navigate. Okay, do we want to walk through the questions?
Yeah,
Yeah,
let's do it. Okay, so first, let's find some putative analogs. So here I'm only going to do one of the tasks. Let's find a putative analog of arylomycin. So how we might do that, I'm going to go back to my status page for the classical molecular networking job. And how we might do that is we go to view all clusters with IDs. And so then in our library ID search bar, we might put in Arilo and search for that. And so we can see we have arylomycin A1 through A4. What we can do is click on our View Network button, and this will bring up the arylomycin subnetwork. So if we put our library IDs on there, you can see there's a few arylomycins there. One easy way to, I guess here you can sort of say putatively, these are probably all analogs of arylomycin. But if you want to sort of see maybe what modifications have happened to these nodes relative to arylomycin, what you might do is label your edges by the delta M over Z. So here we can see this arylomycin A4 has a delta M over Z of 28 relative to arylomycin A1. This could be sort of, you know, two methyl groups. Here we have another one that's a difference of 14 with an unknown node. So we might say that's a methylation. So you can kind of see a few different analogs here. So I'll leave you to, I guess, go through and sort of figure out maybe what these other analogs might be. Okay, so another question would be, which organisms were these compounds found in? So to really easily visualize this, we're just going to draw our pies onto this. And so we can see that here, this putative, I guess, methylated analog of arylomycin is only found in that Roseospora strain of the Streptomyces. So it seems to be unique to that strain. So I guess I'm going through these quite quickly, but I'm hoping that everyone is following. Please tell me in the chat if you need some extra clarification. What happens? Oh, so if all of the nodes within a subnetwork are unknown, you know, that's tough because you can't propagate the annotation necessarily, but that's where maybe in silico tools might come in handy. And we're gonna do some workshops on some new in silico tools, I think, in the future. So yeah, so that's sort of, I guess, what I would recommend if your subnetwork doesn't contain any annotations.
Yeah, so not only in silico tools, you might be able to find sub-fragments of parts of structures, but even the deltas have quite a bit of information. So for example, here you see 12, 14, 28, 16, etc. To me, that suggests that you have patterns of methylations that are different. If it's oligosaccharide, you see 164, 178, 183. So you can start to recognize that there are substructures sort of associated with some of these molecules. Of course, that requires quite a bit of expertise, but the more you look at these kind of mass shifts, the more familiar they will become. Oh, what's a delta over Z? That's the difference between the parent masses of the two spectra that are being compared. So if you have 100 Dalton and 114 Dalton, there's a 15 Dalton difference. In this case, she's pointing to 42 Dalton difference, which is the equivalent of 3 methylations. So that's what delta M over Z means. And so when you do spectral alignment, and you have a mass difference of 42 Daltons between the parent mass, now you consider that when you do the alignment between the spectra, you consider those 42 Daltons as well. And so you get a good alignment even though the molecules are different by the parent masses. Did that help, Elman? Great.
So in case also, Emily, there's like so many features that, anyway, so if you want to look at a histogram of the deltas, it's all there.
Yeah.
Or if you want to highlight, imagine you're looking for only methylations, like 14, you can highlight them as well. So
14, yep. So you can highlight in red which ones are methylations, for example. But yeah, here's the histogram button where you can also see the common M over Z deltas within the subnetwork. So here you can see that 16 Daltons is sort of the most abundant M over Z difference.
Yeah, if somebody wants to create a low-hanging fruit paper, nobody has created a network with these delta M over Zs. And what's really interesting about this is that this actually gives insight in terms of sort of often the chemical classes. So oligosaccharides will show up very nicely, lipid modifications will show up nicely, and peptide changes will show up very nicely. So if somebody's interested in creating a low-hanging fruit paper, you can run with that. Yes, you can look at phase 2 metabolites also. So this is a really cool way. So drug metabolism is here you have unlabeled ways of looking at drug metabolism. I'll try to quickly grab a few papers and with some links to highlight sort of first examples of some of the modifications of drugs.
Okay, so our last workshop task then is to find, I guess, novel derivatives of the stenothrysin GNPS compound, which is shown on the right. So we know that it produces a core ion that, or of M over Z of 853. So if you recall how we did that back in the data visualization section, what we're going to do is go back to our status page. We'll go to view all clusters with IDs. And here we'll search for steno. Okay, we see the stenothrysin GNPS 2 library ID. So what we're going to do is go to the view network button of this. This will bring us to the subnetwork of that stenothrysin GNPS compound. There it is. So now what we can do then is click on this download button here. Can everyone see this? Okay, click on the download button and then we're going to do an M over Z of 853. And then click on this refresh. And here you'll see that the nodes with this common 853 fragment ion are highlighted in red. So you can sort of putatively annotate those as derivatives of this novel stenothricin GNPS analog. Okay, so that concludes the workshop tasks at the end. So we'll turn it to some more questions if there are any.
Well, if there aren't any questions, wait, I gotta look at the schedule. I don't know what's next week. So we just, so you all know,
I think redo is next week.
Okay, so there's a question, but we'll just really quick. We have a schedule on the GNPS documentation. There's a workshops link. So next week we'll be going over redo. So this will be a tool that helps annotate all the public data, saying, look, this public data is from bacteria, this is from skin or whatever, and ways that we can use that to reanalyze public data, co-analyze our data with public data, and where kind of it, it helps with mass and things like that. And then we'll be going over feature-based molecular networking the following week, how to use MZMine, how to use it on GNPS after you've done the feature detection. And then beyond that, a few other workshops on ion identity networking. So that's another thing that builds on kind of these features. But yeah, so there's a lot of things coming up. There's a question about pure compounds. The message that we should run. What is... So if you have pure compounds and you want to gather MSMS for it, first, there's several ways of doing that. You can just inject it one compound at a time, and then just have your standard data-dependent acquisition go. That's totally fine. Generally, we also have some methods for thermo instruments that we published that make the acquisition really, really fast. And there, again, we just use kind of simple data-dependent acquisition. It generally works because the pure compounds in there are super abundant, so it's always going to get the MSMS for those. Kind of downstream to that, we have a workflow as well. It's called MSMS Chooser that makes it a lot easier for you to take that data, extract out the molecule of interest that is the compound that you ran, kind of automatically if you give us the structure, and then we'll make it a library. So that should be relatively easy. We actually have we did a workshop on this a couple weeks ago. There's a tutorial video. But if you all have those, highly encourage you to, either run them, or if you already have them, try to upload it. I swear it's relatively easy. Just because then in the long run, it will help you annotate your compounds from data off of your own instrument. So you can save time. So for those of you saying, I don't have any IDs to my networks, this is one way that you can, help yourself. I mean, it helps the rest of the community, but whatever. But it'll help you. So just kind of, that's one of the things we'd recommend. I think Peter put a lot of publications there. One thing I wanted to...
Yeah, those are for drug metabolism.
Oh, drug metabolism, okay. So hopefully, yeah, that helps. One thing I wanted to show really quick, and it's kind of not done yet, but we're always a work in progress. So it might be a little bit confusing for you all to find where the tools are on GNPS. There's a screen, but there's like a lot more tools than we actually have done workshops on, or actually on the splash screen for GNPS. So if you go to the documentation at the very bottom, we've created a GNPS tool index. And so this is a little less user-friendly, but for those of you getting more familiar with GNPS, this might be a better way for you to actually find the tools, especially some of the newer ones. So we list all the workflows that we have. We're still filling in the documentation, source, and citation. If you want to help with that, let us know. And there's actually a little edit button in the top corner for any of the documentation. And then also some of these web tools that are integrated, as well as community tools that we integrate with. So just plugging that, please help out. It'll help us, it'll help you, it'll help the community. And so that'll hopefully help you find the tools as well that might help analyze your own data. It's kind of grown into a monster, so don't try everything all at once. It's probably not a great idea, but at least it provides you a way to, you know, find maybe what you're looking for. So. Any other questions, comments, concerns? Okay, now is the time. Speak now or forever hold your peace, at least until next week. So thank you all for coming. Thank you all for showing up and participating, asking great questions. And thank you to the organizer, like Emily and Morgan did all the work putting this together. I just get to speak first and last. So, but no, they're awesome and did a lot of work to just make it kind of run seamlessly. Definitely check us out on the next couple weeks for the workshops. And also we have office hours on Mondays at 2 p.m. Stop by if you have additional questions following up from the workshop. There's the forum, ask questions on the forum. And if you see any bugs, we have a GitHub page where you can add issues, then we can fix it there. Again, we roll out new versions every 2 to 3 weeks. So release 21 is coming up. So look for that change log. There'll be some nice quality of life things, I think. We'll see. But anyway, thank you all. We wouldn't be here without you, and definitely let us know how we can help in the future.